Good morning, good afternoon, ladies and gentlemen. Welcome to the WinGD webinar about the NOx new regulation amendment update. So today we will provide you will learn more about the upcoming NOx regulation, so the latest updates, and also a little bit we go into details on XDF 2.0 compliance. You might know that WinGD recently issued a letter confirming the full compliance with the new regulation. And in this webinar actually is the great opportunity to explain why the XDF 2.0 meet this requirement. And also we show a little bit transparently what are the NOx emission that we have. Marcel prepared some very good slide about that. WinGD continue to support XDF 2.0. Actually, we are continuing the development of the engine. Recently, we launched the VCR as an additional incredible technology that give to this technology an additional age. So a quick look on the agenda today. My name is Carmelo Cartalemi. I'm head of global sales. I'm giving this introduction speech. Follow me will be Dirk Hadau, our senior regulatory affairs expert, and he will provide the overview of the revised NOx regulation. Then our Marcel Ott, our general manager application engineering, will explain you the ISER concept, the XDF 2.0, what is unique of this our technology, and also he will show you our level of NOx emission. But then let's get started. Let's go to the live of this webinar. Just few couple of information. This session will be recorded, so you will have access later on to it. Also, the material will be shared. We invite you to ask your question. There is a question and answer button. So in the chat box, please answer your question. We try to reply after the presentation. And in case we cannot do it, we will send you a reply later on. So now I hand over it to Dirk. Dirk, the floor is yours.
Yeah, thank you very much, Camilo. So very warm welcome to all of you. Good morning, good afternoon, or good day to all. And now I start sharing the presentation slides. So that should be the one. Please complain if you cannot see them. So these are my presentation slides. I will start giving you an overview about the revised regulation. Sorry, there was, so now. So that is the brief overview of the contents. So I will start with a short overview and the timeline of what was going on, then a summary of the main points of the regulation, then mentioning what is a rational versus an irrational emission control strategy, and then introducing you the concept of the not to exceed zone, and then the multi-engine operational profiles, ending with a short conclusion. That is an overview of what has happened in the past related to this topic. I will not go into detail for in all aspects here, but mention you only the main points here. So it has started in 2016 with a submission by Norway related to multi-engine operational profiles, short MEOPs. And it was then later extended to cover also the not to exceed zone concept. And there were many discussions at IMO, mainly in PPR subcommittee. And this was ended in the end by a common proposal by US, IMRES, and Euromod, where all the engine manufacturers and designers, as we are participated in as well. So that was a common agreement, a proposal which was agreed at PPR in 2024, beginning of 2024 this year, and then recently approved at MEPC. This was then released in a in an IMO circular where you can see all the details of the regulation. There are other additional information papers here, which I've listed here, and in particular this webinar, which was held in the context of PPR 11 by US and IMARES and Euromod. And that I will also use in my presentation here with some illustrations from that one. And this will be entering into force in March 2027. So that is a brief summary of it. So first of all, I would like to highlight here that these new requirements are rather clarifications of what is already considered to be existing regulations. So it will not change the stringency or lead to stricter rules as we have it now. It's more a matter of clarification of existing rules, which you will see also in the course of this presentation. So what will be added is some documentation effort as what is then called the NOx certification pack. There we will have to describe our base emission control strategy, then also the auxiliary control devices, which we already do now, but then we will have to do it in a little bit more detail, and there will be an extended definition of this ACDs, such that we will have also to declare additional ACDs here. But that is what we are going to support, of course, our licensees, engine manufacturers in that regard. What is important to note here, there's this discussion already in the existing regulation about a rational versus an irrational emission control strategy. So you should have a rational emission control strategy, and you are not allowed to have a so-called irrational emission control strategy. That applies already now, but it is in the current regulation not further specified what this means. So for that reason, there was a screening tool introduced, which is this so-called not to exceed zone concept, which should cover this better for the one who's screening such a control strategy. In addition, in the revised regulation, it is more clearly regulated how multi-tunings, or in IMO context, it's called multi-engine operational profiles, are regulated, and they will be allowed in by a worst case, or sometimes also called an envelope concept. In addition to that, there were also some modifications for test cycles, but these would not change the application for our engine categories. That is maybe the main point behind to adding these a more detailed screening option for the controls, emission control strategy. Here on the left, you can see an illustration of a rational emission control strategy, and that, just to mention that here, is just an illustration which was in particular was specifically designed for this presentation by US and others, which was held for the IMO. And here you can see that between the different 4 mode points, here you have the speed and the power plot. That is the ones which we, as you all know, are certified during a shop test, and that in between or going beyond, it will react smoothly. That is what is called then a rational emission control strategy. And here, that is, just to highlight that again, that is not an existing engine, but that is just an illustration of how an irrational emission control strategy could look like. So here, it would only be, it would be very low specific NOx emissions around the 4 mode points, and much higher emissions in the rest of the speed power plane. That would mean that these 4 mode points would not be representative for the emission behavior of the engine. And that is what it should be. And to solve that, this new regulation or revised regulation was coming into place to solve this and to give the administration some screening tool to check for such control strategies. And that one is the so-called not to exceed zone concept, and that I will describe in the following slides. So first of a not to exceed zone concept is to define the zone. Here's an example of such a zone that is in the speed and power plane again. And here you would have, for an example for a propeller law operated engine. And that would be an example, could be a large slow speed engine operated with a fixed pitch propeller. So you would basically very narrowly around the propeller curve would operate there. And what is important to know for this not to exceed zone, you would have to specify it. It will be specified by the applicant, which is typically the engine manufacturer, and of course would be then supported by the engine designer in our case. And it should cover all the steady state operation points should be covered in this in this zone. And it is cut by this 25% power line and 63% speed line, which then that is important, which US and IMRS were very often mentioning, that this would of course not mean that your rationality of your emission control strategy would stop here and you could do whatever you like. You would still have to follow it. Only this screening criteria would not be applied in this regime. What that is maybe what you would consider the most important is what is now the criteria, the limiting values in there, and that I will try to make it here try to make it as short as possible here. So you would have on the mode line, you would apply a factor of 1.2 of the values you measured on the mode line. And for tier 3, you would add 25% of the limit value to the value you measured on the mode line. So that would be, in our case, 25% of 3.4 gram per kilowatt hour, meaning 0.85 gram per kilowatt hour. That would be on the mode line, which is illustrated here in this very thin line. And then at the edge, you would get a factor of that would be increased to a factor of by a factor of 1.5, and you will get an additional factor f beta, here fb, which accounts for the fact or accounts for the amount you are below the is your cycle average below the limit value. So assume you would have only you would only have for tier 3 1.7 gram per kilowatt hour. That would be only half of the limiting value. That would grant you a factor 2 here in addition to this 1.5. So, and that is also illustrated here. You see that for that is now the speed and power plane. So you would have the you see along the mode line in the middle, that gives you some margin here, this 20% margin, and then a higher margin at the edge if you go towards the edge. And here, again, that is a summary of that one. Here, that is a bit more detail. How you would determine these values. So that is again the speed and power line. Here you would have the mode points, and to determine now for that point here, the limiting value, you would first have to interpolate your emission value measured at these two mode points. You would receive the value here, that would be this N, what is called now Ny. That you would then multiply by the factor 1.2 or the other criterion for tier 3 accordingly, which will give you this NLY. That would be at this point the limiting value, and then you would have a limiting value specified by this 1.5 times the value would give you the value here, and then you would interpolate between those two points to receive the limiting value for that point here. And that would be then the limiting value at your checkpoint, which you would have to cope with. So as mentioned, we have in addition the multi-engine operational profiles, which are covered by the regulation. And that is sometimes called multi-maps or tunings. Here I have an illustration which I took from the same presentation by US and others. And here is an example of 4 engine operational profiles. And that is now plotted the load versus the specific NOx emissions of each of these individual operational profile. And you can see that they have different values here, and and they even cross each other, so that some are at some loads higher than the others. And in the new regulation, it is it is clearly regulated that you have to take the highest value of each, and that is due to the reason that the operator can switch freely between these modes here. So in principle, if this would be specified differently from that, he could use switching between the modes to circumvent to be in line with the requirements of the NOx emission regulation. That is the reason why this is like this. And this is, as mentioned, and already considered basically now, not directly specified in the regulation, but indirectly covered by having the concept of rational emission control strategy, not allowing an irrational emission control strategy. And the good thing about this is that for that reason, we are with our engines are already fully in line with such a worst case, or sometimes called envelope concept. That is the conclusion of my presentation already. And here I have the same summary again at the end, just to remind you what I covered in my presentation. And with an addition here mentioning that to highlight that we are already now using a rational emission control strategy, and we are thus fully in line with these upcoming revised rationality and MEOP requirements. That would be my part. Thank you very much for your attention, and then I would hand over to Marcel, who would give you a bit detailed insight how this applies to our engines. Thank you.
Thank you very much, Dirk. Welcome, good day to everyone also from my side. I'm very happy to have this opportunity to not only present you an update of the rules and regulations that Dirk just did, but we would also like to give you an example of how and why our XDF engines are and remain NOx compliant with any of the rules that have just been discussed. Before we head into that, I would like to remind you again that if you have questions, please type them in the Q&A section of Teams. So we'll see your questions and hopefully be able to answer that at the end of the presentations. So let me move on with that. presentation. First of all, regarding NOx compliance of our XDF engines in general. So the situation that we have now, as Carmelo has also mentioned at the beginning, is that the announcement of our competitor, particularly to remove the low pressure Otto cycle engine, the Mega, from their portfolio, has actually created some interpretations or perceptions in the market that Otto cycle engines would in fact not be compliant with the updated NOx regulations. The rules and regulation changes we have seen from Dirk before, and we would like to give you some of the fundamental insights and basics here. And first of all, confirm very clearly that our XDF engines remain fully compliant with the NOx rules and all the changes or the updates that are to be expected now. Secondly, we can also state, it's fair to say that the lean burn auto cycle combustion process is in fact by nature the process that reduces in the least possible NOx emissions. So if you talk about a low NOx or the lowest possible NOx engine, it's actually a lean burn cycle combustion, which as you can see from the illustration here, typically produces about 30 times lower NOx emissions compared to any diesel cycle combustion engine. So that can be a diesel engine, or it can be a high pressure dual fuel or natural gas engine that works according to the diesel principle. But what they have in common is that diesel cycle engines always have a NOx BSFC trade-off, which means that the higher the NOx, the worse the BSFC, and vice versa. And that is one of the fundamental reasons why they're typically also tuned to be close to the NOx limit, which in that case is tier 2. And you see that the IMO limit there is 14.4 grams. So engines are typically close to that. While you see the example of our XDF 2.X engine here, that typically has NOx emissions of 0.5 grams per kilowatt hour or below, which is far below the regulatory limit, and which, as I mentioned, is about 30 times lower than a diesel cycle engine. So just very generally, to assume that the upcoming regulations would try to somehow penalize the best-in-class engines, I think that is somehow strange, and it's clearly not the case. A number of parameters are impacting NOx emission or NOx formations of the lean burn engines, and this is only a list of a few of them, some of the most important. Engine tuning, of course, impacts NOx emissions, and that's also the reason why these kind of screening principles have been or are going to be introduced now to make sure that the tunings are rational also in between the IMO load points that are measured. Scavenging has a very important impact on a lean burn engine because you need to have a properly scavenged cylinder to achieve good combustion and emission management. And that is very closely linked to turbocharging efficiency also. So you need to have a good turbocharging efficiency to effectively scavenge and clean these cylinders. And then another very important factor on, let's say, the latest generation engines with exhaust gas recirculation systems is the amount of exhaust gas that is fed back to the combustion. So the EGR rate, as we call it. So how much of the exhaust gas is fed back into the engine again. And we see that high EGR rates are necessary for a good combustion control when running on gas on an engine with a high compression ratio. And that is a fact that we would like to highlight and explain a bit more in detail. In fact, this is also one of the areas where we do have a conceptual difference to our competitors' product that clearly plays in our favor in this case. So let's have a look on a few of the fundamentals of the different EGR systems that are applied on our engine and on the competitor's Mega engine. And I think it becomes clear here that there is a conceptual advantage of our ICER system, as we call it, so our low pressure EGR system, versus the high pressure EGR system that our competitor applies. To the left here in the illustration, you see an overview of the ICER system layout, and you can see here that we take some exhaust gas after the turbocharger turbine and feed it back through this recirculation loop back into the engine. That means, as you can see from this layout, that there is always the full exhaust gas flow across the turbocharger turbine. So regardless of how much exhaust gas you recirculate, there is always a full flow of it through the turbine, and that ensures the highest turbocharging efficiency in all modes, in gas mode, diesel mode, but also if the EGR is or the ICER system is switched off. The system also allows us to run very high EGR rates, so we're using something around 50% of the exhaust gas flow on a let's say a regular ICER engine. On engines with ICER and VCR, our latest specification, we use up to 65% of the flow that is being recirculated. And that leads, as we have seen from test results and our simulations, that clearly leads to the best possible performance and efficiency, because it allows to maximize the compression ratio and achieve the best results. We have also seen that for gas combustion, a minimum EGR rate of 40% is necessary to see a reasonable impact on the combustion. And this is one of the areas where our competitor system clearly suffers, and that is has always been our position here about the let's say the technical feasibility of this system for a lean burn gas engine. So what we see here on this illustration is an overview of the high pressure EGR system, how it looks like. And you can see here that it comes with a fundamental conceptual disadvantage of the fact that any kind of EGR rate that you have is kind of bypassing the turbocharger turbine. So as you start to recirculate exhaust gas through the EGR line, the flow on the turbine is being reduced, and the power on the turbine is also compromised. So that leads to a compromised scavenging, and that's one of the major fundamental disadvantages of this system. Furthermore, this let's say this limits the EGR rate to approximately maximum of 30%, which, as I just mentioned before, is seen as insufficient to run on a reasonably high compression ratio and achieve competitive performance figures. In case you want to run on a high compression ratio anyhow, that means that combustion stability would become an issue because of the lack of EGR rate. And that in turn requires to inject some diesel, a certain amount of diesel, to stabilize combustion in all operating regimes. Then, of course, injecting more or an increased amount of diesel will have an impact on NOx emissions. We don't want to speculate here how this affects the compliance and competitiveness of our competitor product. But just here to show the conceptual differences between the two engine types and a possible explanation for why we believe our XDF engine has conceptual advantages here to be compliant. We would also like to give you a few examples of actual NOx measurements of actual engine series, production engines, and explain why they're compliant with the new upcoming rules. So what you see in this graph here is NOx measurements on some of the load points of 3 different engine series of the same type. They're all X72DF 2.1 engines, but built at different manufacturers, so different test beds with different measurement equipment. Obviously different testing conditions, ambient conditions, gas qualities, and so on. So 3 different series of engines. And you see that NOx emissions, they vary to a certain extent between the 3 full lines at the bottom. They vary because the engines have different rating, as said, different ambient conditions on different test beds, different measurement equipment, gas qualities differ between them. But what you can also see is that the level of certified emissions, so the IMO average levels, are significantly below the tier 3 NOx limit. Again, the tier 3 NOx limit is at 3.4 gram. You see that dashed line to the right, while the engines are certified with NOx emissions of 0.2 to 0.4 grams in this case here. So very much below the NOx limits overall. What we also see is that we have a good margin to what we call the rational NOx limit here for points between the IMO load points. So the dashed curves that are drawn on top of the measurement lines here, they indicate the maximum level of NOx emissions that is allowed in between the IMO load points to still be considered as a rational control. So as long as any of the additional measurements in between load points is below that limit, the control strategy is considered to be rational. And you see we have a very good margin to that. There is actually no reason why we would have to exceed this rational NOx limit for any reason. We have applied fully rational control strategies on all our WinGD engines. That's a general principle that you can count on. And with this, we can confirm that even the current control strategies, what we have now and what we had applied in the past, is fully satisfying the updating regulatory requirements. Furthermore, a second example here, and this is another NOx measurement example that we would like to use to explain to you the compliance of our engines, also with this not to exceed zone concept that is new or has been described in more detail, as we saw from Dirk's presentation. What you see on this slide or on this chart here is an emission measurement example of one specific particular engine running on different propeller curves. So we have the nominal propeller curve, first of all, the green curve that you see here. This is let's say the nominal curve that the engine is tuned and laid out for. Then we have a couple of other lines that represent heavy running with approximately 20% higher torque. So that's the orange line here. And this 20% additional torque above the propeller curve, or the nominal propeller curve, represents a case with heavy PTO usage, for example. On the other hand, we have a light running curve, the light blue one, which shows the results with approximately 30% lower torque. So this covers quite a big envelope that we have also seen in some of the regulatory illustrations from Dirk. And what you can see here is, interestingly, that the NOx emissions, they do not change much. They are quite well in line, regardless of how much torque the engine produces. And that is a matter of tuning, first of all. Of course, we need to make sure the tunings are done correctly and fully rational. Again, that same terminology. And we also have to make sure, or we did make sure, that we have the right, let's say, principles and systems in place. So some people are concerned about heavy running operation with PTO, that this would produce higher levels of NOx emissions. In fact, what happens here is that this is not necessarily the case. What happens is when you run with higher torque, with PTO, for example, the fuel demand increases. We get more exhaust gas power to the turbocharger turbine, which leads to a higher scavenger pressure. And the higher scavenger pressure, again, stabilizes combustion, allows to run with the best possible air-fuel ratio. Again, for this, you need to have high turbocharging efficiency, and you want to have the full exhaust gas flow on the turbocharger. So don't waste it by bypassing the exhaust gas from the turbine. So that's naturally, again, an advantage of our ISO system. Additionally, what the ISO system does is that it also continuously monitors the combustion speed, so the actual combustion of the engine, and it adjusts the EGR rate based on that. So if it sees that the combustion starts to deviate from what it should be, it starts to adjust the EGR rate, and by that it also stabilizes the emission behavior of the engine. So even if we have varying torque operation, the NOx emissions are not affected to a great extent and remain fully compliant with the limits. Again, to outline here that we do always use fully rational control strategies. And as you see from this example, the engine remains fully compliant with the rules and regulation, also when operating besides the nominal propeller curve. A few more words here on the general competitiveness of the VCR or the XDF engines, and would also like to spend a couple of minutes on explaining you some of the newest or the latest steps that we made with our VCR variable compression ratio system. And as we were talking about the engine tunings and other aspects here, I think this is also worth to mention because the VCR provides an additional dimension in how we can tune the engines to allow to achieve best possible efficiency and emission levels throughout different ways of operating the engine. So this VCR system that I think many of you are aware of leads to further reduction in gas and diesel mode consumption, and it further reduces methane slip, while NOx emissions can be fully under control under all operating conditions. Here is an example of a comparison to the mega figures. Obviously, that is not so relevant anymore, but we have been asked by many customers how we look in that respect in comparison. And as you can see from these graphs here, to the left is gas consumption, to the right is diesel consumption, specific consumptions. This engine, latest specification with ISO and VCR, results in about 6.5 grams or 5% lower gas consumption compared to what the Mega used to have specified. In diesel mode, the advantage is even bigger. There it's 8% or 13 grams lower consumption. So it's a massive step in comparison and a significant improvement in efficiency. And then that also obviously turns into CO2, lower CO2 emissions. With this, we are actually outperforming all other propulsion system types, also including high-pressure dual-fuel engines. Also, specifically when looking at LNG carrier applications, I think none of the systems that are available or being discussed do provide similar efficiencies, comparable efficiencies than what we have with this released product here. So please talk to your shipyard, your engine builder, or to us about this technology. This also brings me to my conclusion slide of this second part here, and I would like to reinforce that our XDF engines are fully compliant with the upcoming rules. and that there is no reason to worry about that. As we have seen from Dirk's part of the presentation, the update of the NOx regulations is actually mostly related to methods for screening against irrational controls. So it is a measure to have a possibility to find irrational tunings or controls on engines. And as our engines have always been tuned according to rational control strategies, this does not impose any direct consequences to our engines. So there's no additional limitations or no need for adjustments of tunings or any hardware settings on our engines. And also fuel consumption is not affected. We often get the question now, how does that influence fuel consumption? But since the tunings do not change, we have had these tuning strategies already before, there is actually no impact on fuel consumption that results out of this update of the rules. Our engines, as we saw, remain fully, let's say, or to be the best, most competitive solutions with the best performance and emission footprint. Overall, we're very confident with that and proud with our latest steps that we have made there. Also, when it comes to the VCR system, that further improves performance advantages to any other alternative systems or engine types. And if we want to keep that very short and very simple, I think we have seen from today's session that the rules are fairly complex. They're not very easy to understand at first glimpse. But the solution that we have is very simple with the XDF that is and remains fully compliant to any of those rule sets. So with that, we come to the end of this second part of the presentations, and I would like to hand back to Carmelo to moderate the Q&A sessions. I hope we have received a number of good questions in the chat box. Carmelo.
Indeed, we received many interesting questions. First of all, thank you, Marcel and Dirk. Excellent presentation, very clear. Let's get started. The first question we received is about retroactively of this regulation. So, what if an engine is tuned with a rational control strategy, as shown in the right graph, what Dirk showed before? What will be the consequences, especially for the existing fleet? I don't know if you can, Marcel, want to take this?
I think on the regulatory aspect, I would leave it then to Dirk to say something about that. I think when it comes to our engines and our products, there is no such case because the engines have always been tuned according to rational control strategies. So there is no, let's say, such engines in the field that would not be compliant here. When it comes to our competitors' engines, we don't know. Of course, the question would need to be asked to our competitor. From the rules and regulations side, I'm not sure if Dirk has an opinion if this will have any impact.
Yeah, thank you. That is indeed a good question. So the revised regulation is not meant to apply retroactively as such. But on the other hand, of course, if there would be some case where it would turn out that it was an irrational emission control strategy, that could still be considered, but I don't know, to be honest, how that would be considered, and that would already be the case now. So that is not changing, so to say, that behavior. If there would be someone with an irrational emission control strategy, would already, with the existing rule, be not allowed. And then, of course, if it would only turn out later, I don't know what happened. I think there has not been such a case yet. And as Marcel mentioned, that will be not the case for our engines anyhow.
Very good. Another question very interesting is about, we talk a lot on this presentation about XDF 2.0, but the customer asks, what is about the compliance of XDF 1.0 without ICER? Marcel?
Actually, it's the same there. I mean, we have been focusing on the 2.0 here in this session because we see it's clearly the most competitive solution in terms of performance, and it's also what we sell the most and what is, let's say, the shipyard's standard designs. That's why we had focus on the 2.x engines here. For the 1.0 engines, the principles are the same. The control principles are fully rational, same as for what we discussed today. So there is no specific reason why there would be more of a challenge or a problem in that respect.
Also, a very interesting comment, more than a question. It says something like, it will be also essential to compare the NOx emission and explain the difference between high pressure two-stroke, so the MAGI, with XDF 2.0. Maybe Marcel, just elaborate, what are the difference there?
Well, the high pressure two-stroke, I assume that's the MAGI concept that is in question here. The differences generally are that the MAGI high pressure engine obviously works according to the diesel cycle combustion principle, also when running in gas mode, while the XDF is a low pressure auto cycle combustion. And there is a very big difference when it comes to NOx emissions of these concepts, which is directly linked to the combustion principle. So while the lean burn low pressure engine burns the gas in a pre-mixed, let's say, homogeneous, relatively cold environment, it produces very low NOx emissions. The high-pressure diesel cycle concept instead burns the gas in, let's say, the jet of gas that is entering the cylinder at locally stoichiometric conditions. And that leads to very high flame temperatures, which again lead to high NOx emissions. And that's the main reason why we see, as we saw before, approximately or typically 30 times higher NOx emissions for a high pressure engine compared to the low pressure. So it's a difference that is fundamentally related to the combustion principles.
Maybe we can say that XDF 1.0, 2.0 are tier 3 in gas mode, whilst MAGI in gas mode is only tier 2. That is also the result of what Marcel basically said. Very good. Thank you, Marcel. Another technical question about the regulation. One Greek customer asked about clarification, the paragraph 3.3.5. In short, I try to read this. For member engine of engine family of engine group first certified prior to the entry into force of the requirement under this section, demonstration of compliance with the requirement of this section may be on the basis solely of documentation which is to be acceptable to the administration. I think this is very similar to the first question Dirk you answered. Do you want to comment this?
Yes, I can comment this. That is typically, let's start with how it applies for our engines. Typically, it would not apply for our engines because that is for engines where you do parent engine tests, typically for a wider group or of typically a family. So you do your parent engine test at 1 year. Let's say that was in 2024 this year. And now we have, you would certify member engines several years after that. That is typically the case for the four-stroke engines, where they cover a larger range with different ratings in one group, which we typically do not do. Then they have then they still have to show. I think that would enter into force only for member engines from 29 on, that they have to show then that they are with these member engines come in line with these rules, but they don't need to have additional testing. That is rather why this additional paragraph is there. But typically, as we have typically a parent engine for our smaller series, that would not affect us.
Very good. Thank you, Dirk. Very good. Another question we have seen is about the compliance of the engine in diesel mode. We focus very much on gas mode. Actually, the reason was because the letter we received from competitor put in discussion the Otto cycle. Anyway, one customer asked Marcel, what about the compliance in diesel mode?
Compliance in diesel mode is also uncritical because it's basically the same principles as on any diesel engine there. And the main impact of the regulation or the regulatory update here is to actually avoid any inconsistencies in the tuning between the mode points. And as we discussed before, we do apply those fully rational strategies throughout our portfolios, and that is obviously valid for diesel mode operation of an XDF also. So essentially, it's the same as on a regular diesel engine. There is no any difference in that respect with the XDF.
Very good. Let's take another couple of questions. Now we receive many questions just last moment. One customer said, Marcel, related with the latest statement, the XDF engine provide less consumption compared to other engine, including high pressure Maggie. Can you please provide the comparative data to demonstrate the same? I think that is a hot topic, Marcel. We have time to send a complete comparison, but just if you can pitch shortly how XDF 2.0 with VCR is competitive against Maggie.
As you say, Carmelo, we can of course send some more complete data and comparison related to this point. In very short, what we see now with the latest specifications of ICER and VCR engines is that in terms of efficiency, we are very similar to an MEGI in gas mode. In tier 3 mode, we're much better because we're inherently tier 3 compliant, while the high pressure engine is not. And that comes with a consumption penalty. And then if you also include the let's say electrical power demand of the different solutions, then our engine is typically much better off if you look at the overall plant system to produce the electric power demand that the engine has for fuel gas supply system where it needs more power than the low pressure engine. For tier 3 measures, EGR blower where it needs more power. So if you look at the overall vessel setup, our XDF 2.0 VCR is typically the best in class.
Thank you, Marcel. Let's say now focus on the NOx regulation. Another question we received about the set of NTEZ, not exceed zone, within the maximum engine operation range. The question is how to define this zone is within the range described on our MIM. Dirk, can you explain how the NZ is defined?
Yeah, so this zone should cover all continuous operation, means steady state where you can operate continuously. That should be covered by this zone. That goes according to our MIM to the upper limiter for that and also down below where it can operate in continuously. So that should be, and that is, let's say, not an issue for us to cover that, even with the NOx emissions, as maybe that is so as you have seen at the mode line, we have some margin with the screening tool, but if going away, that you will get even an increased margin. And if you have a rational emission control strategy, meaning that you are not trying to then change your control strategy when you go away from these mode points, that you would not be out of compliance, or you would not go beyond those limits. This can solve the question. Yeah, thank you.
Thank you. Then a very interesting question. I think a very appropriate question is about if WinGD has a plan to change the consumption tolerances in case the NETZ is applied. Marcelo, can you answer this?
Maybe I can answer to this. Actually, we have no intentions to change any of the consumptions. As you may know, also the consumptions that are stated in GTD, in our case, they're actually related to propeller mode operation, so operation on the propeller curve. If the engine operates outside the propeller curve, there is already now a slight, let's say, difference in fuel consumption is not significant, but we do not see any changes in that and any necessity to change consumption in GTD as a result.
Very good. There is another question about, it's not really on this topic, but to talk about methane slip comparison, especially with the competitor, we assume Mega or Maggie. Even though it's not really appropriate, I think it makes sense that Marcel, maybe you can pitch a little bit where we are now with methane slip and how the overall emission our engine, especially in some application, are very competitive, actually even lower according to some evaluation. Can you elaborate a little bit generally?
Yeah, we can, of course, add into that also a little bit. And I didn't mention it today on the slides because it was purely, let's say, focusing on NOx emissions. But also when it comes to methane slip, we have made significant progress on our latest engines. So with ICER and particularly also with ICER and VCR, where we achieve methane slip figures of a weighted average, say, below 0.8 grams on many of the engines. That means that the methane slip becomes, let's say, very low, and the impact on methane slip on the CO2 equivalent is fairly small also. It is a matter of fact that the methane slip of the main engine alone is still slightly higher compared to a high pressure engine. But if we look at the overall propulsion system CO2 equivalent emissions, we are very competitive in many cases, especially for applications with a relatively high electric power demand, like an LNG carrier application. We're clearly better in overall greenhouse gas emissions, even comparing to a high pressure solution that, if you look at the engine alone, would indicate that it should be better, but with the full propulsion system, it's not.
Very good. Last comment, actually very interesting also, is about, Marcel, you have shown that our NOx limit for XDF 2.0 actually is much, much lower than the tier 3 limits. So it seems that in a way, WinGD overachieved the target, and I think that is a well-known fact. Actually, we are below 1 gram. The average is 3.4. Now the question is possible to optimize actually the fuel consumption, gas consumption, if you use the PTO? Do you think this can be considered in the development?
Well, maybe to come back to the fundamentals here of very low NOx emissions and overperforming in terms of NOx regulation, I think that is in a way true. We see that the NOx emissions in gas mode, they are well below regulatory limits. But that's a matter, it's not related to the tuning primarily, it's a matter of the combustion principle and the setup. So when running in gas mode, we by nature have very low NOx emissions. In that regard, this engine could actually live with a much more strict NOx regulation than what it is. But the NOx regulation is coming from diesel cycle engines originally that do have much higher NOx emissions generally. Because this engine doesn't have the NOx BSFC trade-off of a diesel, we cannot do directly, let's say, an optimization of better consumption in trade for a higher NOx. But what it gives us, the possibility it gives us, you mentioned PTO operation, is that we can allow PTO operation with high PTO power without being restricted by NOx limits, because we do have such a big margin anyhow. So there is no reasons to not have or to have limitations based on NOx.
Very good. Time is up. We answered almost all the questions. So I would like to close here and thank you, everybody. We have had a very good participation today. Thank you for your time. Yeah, let's stay in contact. I think WinGD is available for providing all the information you may need. Again, we reinforce the concept that XDF is fully compliant. WinGD is continue to develop this product. So reach out if you need additional question. And with that, I would like to wish you a nice day and thank you very much to Dirk, to Marcel, and to the all supporting us this webinar. Have a nice day.
Thank you. Bye, everyone.
Thank you very much, and goodbye, everyone. Have a nice day.